We often hear that the memory demands of training modern neural networks are being solved by low-precision formats. It is a compelling image, seeing these massive models running within the narrow confines of 8 or 16 bits. The reality is that this efficiency is superficial. Modern frameworks typically cast weights and activations down to 16 or 8 bits solely to maximize the throughput of matrix multiplication hardware. Behind that thin layer of low-precision compute, these systems retain a complete, high-precision float32 master copy of the weights. This replica is necessary to safely accumulate the infinitesimal gradient updates that occur during training, but it functions as a persistent VRAM tax that limits how many parameters can fit on a single chip. This raises a question about the necessity of that overhead. If we delete the float32 safety net entirely, what happens to the network's memory profile and its mathematical stability? True memory efficiency requires abandoning high-precision replicas altogether. We cannot merely mask them behind low-precision operations. We must find a way to train without them. To test the feasibility of training without a master copy, we can examine the down-the-dem research report from the Welvet Go runtime. The report introduces a framework called the narrow truth architecture. In this system, neural networks train natively on sub-byte formats. There is no high-precision replica stored in memory. The narrow storage format is the only version of the weight that exists. This method differs from traditional quantization-aware training. While QAT often simulates low precision while keeping weights in a wider format during the backward pass, Welvet performs in-place updates directly into the compressed storage. Welvet's researchers tested this across 3 variables: native data types, packed quantization blocks, and a full matrix of cross-numeric permutations. This data allows us to isolate the actual storage benefits of demoting numbers from the compute bottlenecks that frequently occur when the hardware has to process them. In a vacuum, we expect a direct relationship between bit width and memory usage. As the number of bits drops, the physical storage payload should decrease linearly. The Welvet payload data confirms this. Moving from wide types like complex 128 to 1-bit binary formats, the footprint drops significantly. Sharp drops at float16, int4, and binary prove the runtime enforces native storage sizes rather than just using a wide container. However, there is a hidden cost to escaping standard 8-bit memory boundaries. Hardware architecture imposes its own floor on how small a weight can actually be. Comparing theoretical bit math to actual bytes allocated in hardware reveals a clear divergence at the lower end of the spectrum. This gap represents mandatory overhead. Alignment requirements, packing headers, and runtime bookkeeping consume much of the space saved by extreme sub-byte compression. Mathematical models of memory savings often ignore these realities. The hardware itself dictates the true floor of payload compression. These floor limitations become even more pronounced when a model is exported for deployment. To move weights from the runtime heap to a disk, the system uses serialization formats like JSON. There is an inherent discrepancy between a raw weight buffer in RAM and the structured text required to represent it in a file. This chart shows the serialization tax. As bit width decreases, the export format's overhead dominates the payload, pulling the purple line sharply away from the weights. When raw weight arrays shrink into the sub-byte range, structural metadata becomes the primary component of file size. Successfully shipping a 2-bit model depends on optimizing both the weights and the container. A dense serialization structure is mandatory, or the metadata overhead will eventually eclipse the model itself. Achieving that sub-byte compression requires a choice between 2 distinct architectural paths tested in the Welvet report. The first is FormatNone, which represents native, in-type storage. This is tested against block-packed formats, such as the Q40 types used in llama.cpp. The left panel compares memory footprints. At identical bit budgets, native float16 and packed Q40 achieve nearly the same reduction in storage size. But the right panel shows training time for packed formats is significantly higher, as the system constantly unpacks, updates, and repacks weights. The label 4-bit tells you nothing about performance on its own. The specific underlying mechanism of compression is what determines the actual training speed. This data challenges the assumption that smaller payloads lead to faster processing. In many cases, shrinking the weights actually slows down the pipeline. We can see why by breaking a training step into its 3 phases. the forward pass, the backward pass, and the gradient update. Notice how the dark red line for total training time spikes wildly at points like uint6. This gap between the stacked bars and that red line represents a severe compute penalty. The system consumes cycles unpacking sub-byte blocks before the math even begins. Because matrix vector multiplication requires wide accumulators to maintain precision, narrow storage formats force the system into expensive host pairing routines. Numerical demotion solves the VRAM capacity bottleneck, but it does so by shifting the strain from the memory bus to the processor. One solution to these bottlenecks is a heterogeneous numeric pipeline, a system where the wait storage type and the activation compute type are intentionally mismatched. Welvet's Cross-Numeric Testing Matrix demonstrates the viability of this approach across a massive range of configurations. The grid tracks 34 unique wait storage types, cross-tested against 15 different activation compute hosts. Every cell in this matrix trained successfully without kernel collapse. This proves that matched data types are not a mathematical requirement for stable learning. In this sequence, a 4-bit wait streams from storage through an in-8 activation host, outputs to a float32 accumulator, and is immediately compressed back into a 4-bit block. Despite the complex journey, this narrow sub-byte state is the only truth permanently retained in memory. The strict coupling between storage and compute is a legacy of software design, not a fundamental mathematical necessity. The narrow truth framework demonstrates that we can overcome the VRAM footprint constraints that currently limit massive LLM scale. We do not need the float32 master copy to maintain stability. However, shrinking the file size is distinct from speeding up wall clock time. To gain actual speed, we need the development of native low-precision GEM-V kernels that can bypass wide accumulation. This benchmark is a proof of concept using synthetic dense networks on CPU backends. It proves the mechanical viability of the approach, but more work remains. The next phase of research must validate task loss curves and optimizer stability on production-scale models running on modern GPUs. Eliminating the FP32 master shows we can fit neural training into incredibly small hardware footprints. But to make those models run fast, the industry must rebuild its fundamental math kernels from the ground up.